Brief demonstration of the Rational Zero Theorem and the Intermediate Value Theorem. This is a statement of the Rational Zero Theorem. If a polynomial has integer coefficients, then every rational zero of the polynomial is of the form p divided by q, where p is a factor of the constant term and q is a factor of the leading coefficient. So let's begin with an example. Let's determine the possible rational solutions for the following polynomial: 4x to the third minus 2x squared minus 7x plus 3. First, we determine if we have an integer coefficient polynomial. Remember, the theorem only applies to integer coefficient polynomials. And in this case, we do. So we may list out the factors. The constant, the number 3, has factors 1 and 3, and that's because it's prime. The leading coefficient, 4, has factors 1, 2, and 4. Now, in order to use the Rational Zero Theorem, we're going to form the ratios as described in the theorem itself. So what we do is we list out all the factors of the constant. That's what's up here circled in blue, and it's labeled with numerators. And the reason why is because these are going to form the numerators of all of our possible rational solutions. Below that, we have all of the factors of the leading coefficient, and these values will form the denominator for each of our possible rational solutions. And what I've done here is I've said, okay, I'm going to take the first number in the list of factors for the leading coefficient, and I'm going to divide it into each number that's in the list of factors for the constant term, and I'm going to form my ratios, which is circled down here in green. Now, because rational solutions could be positive or negative, and the theorem doesn't specify the sign, we have to go ahead and put both a positive and a negative possibility as a guess for a rational solution. So as we can see here, we have 1 and 3 for the numerators, and we have the 1 circled here in red, and that signifies that that's going to be the denominator that I will divide into each number in this list for the numerators, and that's how these ratios start to be formed. So my first guesses to rational zeros is plus or minus 1 divided by 1 or 3 divided by 1. We simply repeat this process, moving to the next number in the list for the factors of the leading coefficient. In this case, that factor happens to be 2, and that's what's circled in red here. So this number circled in red, 2 in this case, will divide into every number that happens to be in the list for the constant term. And when we do that, we get 1 divided by 2, and we get 3 divided by 2. So additions to possible rational zeros are now plus or minus 1/2 or plus or minus 3/2. And again, we repeat this process with the number 4, the last number in our list for the factors of the leading coefficient, and we divide 4 into 1 and 4 into 3 to generate more possible rational zeros. And of course, this will lead to 1 divided by 4 or 3 divided by 4. Now, what appears down at the bottom here is simply just a little cleanup of the possible rational solutions. So as you can see, I've already kind of reduced the fractions down as best I can. And reducing the fractions is common so that the numbers may be easier to test. The complete list of all possible rational zeros is as follows. You have negative 1/2, negative 3/2, negative 1/4, negative 3/4, negative 1, and negative 3. But then you also have positive 1, positive 3, positive 1/2, positive 3/2, positive 1/4, and positive 3/4. So there are a total of 12 guesses as to the rational zeros. Now the theorem specifies that if there are rational solutions to that polynomial, they have to be in this list somewhere. Remember, the theorem suggests that if a polynomial has rational zeros, they must come from the list generated. So if there is a rational zero, it's got to be in that list. A polynomial is not required to have rational solutions. Consider x squared plus 1 equals 0. This is an integer coefficient polynomial whose solutions are I and negative I, not rational numbers, in fact not even real numbers. This theorem, used in conjunction with the intermediate value theorem, can provide intervals to locate roots even if there are no rational solutions. And this is kind of boxing possible roots in when you use both the intermediate value theorem and the rational zero theorem. So if we evaluate the polynomial between the two extreme guesses, negative 3 and positive 3, by the intermediate value theorem, we have p at negative 3 is negative 144, and p at positive 3 would be positive 114. A sign change in the output of the polynomial, we are guaranteed at least one root to the polynomial inside the interval negative 3 to 3, and this is a direct result of the intermediate value theorem. Now we may use the other guesses to help localize roots further. So let's examine the guesses that are closest. The polynomial evaluated at negative 1/2 gives a negative 1.5. The polynomial evaluated at positive 1/2 gives positive 6.5. Because there's a sign change in the output, there has to be at least one root to the polynomial between negative 1/2 and positive 1/2. When we apply solution methods, we find the real solution to be approximately negative 0.36, and this number is, the actual root itself is irrational. Thank you for your time and attention.